Hey guys, if you haven't checked the open pit module on IMAT to evaluate the slope stability of your pit walls, you should definitely do so because it's disturbingly user-friendly, powerful because it uses Flash 3D, and really smooth. I was mainly using IMAT for underground mining modeling because it seriously streamlines my workflow, very easy to set up, and the visualization of parameters and contours are pretty slick. I typically used other software packages for open pit mining, but I was curious about what IMAT could offer, so I give it a try. So in today's videos, I'll show you an example of how to evaluate the slope stability of a large open pit in just a few clicks. Alright, without further ado, let's get rolling. Off by creating a new project. Let's call the project name Open Pit Tutorial. And let me save the file under the folder IMAT files. For the my name, let's call it Open Pit Tutorial. And once we're ready, we click OK. First thing we do is import the geometry under the geometry plugin. Under pit shells folder, I will import the files of interest, which are topo and the pit shells. We start with the topo and we show it in the viewer. So we don't have to convert anything. Then it appears in the viewer. Here we go. Everything looks good. And then we do the same thing for the pit shells. Here we go. And then we don't convert the coordinates. So both the geometries are looking good. One thing we need to do, because the file is in DXF, is to extract the geometry from DXF. This will convert it to STL. We can delete the original file afterwards. So it's very important step so that we can work with those files. Another thing that I advise is to create a folder called data, where we can, or raw data, where we can save all our raw files and geometries, the geometries that we don't really need, but we want them to be in a backup. So after importing these files, as you can see, the topo may require some simplification. So I will go with the target simplification of 25. I leave aggressiveness the default value, and now that I simplified it, I will compare the two files, see if they look very similar, so I can proceed. I changed the color for one and I compare them, they look good. So what I'm gonna do is I like to rename, so I'm just gonna copy the old one into the data row, and I'm gonna rename the topo simplified into topo. I like to rename and my files and keep them clean. Now it's time to import the structures and the geotechnical domains if applicable to your case. So what I'm gonna do is I'm gonna go to structures, import geometries, and I'm gonna go and look for north, south, and the west fault. I don't convert them, and I give it some time to import those features. So if we look at them in the viewer, I'll show them. So two are perpendicular to the pit shells and one is parallel to the east wall. So this one will be tricky for stability, and we will see it later. So one key feature utilized in this process is the shrink wrap. So what it does is that it overlays a simplified gridded surface into the existing mesh and conforms it to the underlying geometry. So the result is cleaner, more uniform triangulation that preserves the overall shape while reducing complexity. So it's very, very important feature. We use it for underground, for CMSs as well. It makes things much easier and it simplifies the geometries. And the good thing about IMAT is that we can batch these operations on multiple meshes. So imagine you have hundreds of slopes or hundreds of structures that are complicated. We could just batch all of them, and they'll be done in a matter of few seconds. The geometry looks good. Now let's go ahead and build our Flag 3D pit project. So let's name it the west wall factor of safety, and click OK. We will use the depth below surface for the pore water pressure calculation, and we will select 5 meters below natural terrain. When we click on the project setting, we get this window, and it's very important to pause here. So you can see here that the solve strategy is custom local, and then the custom local and balance forces is 1E minus 4. So what does that mean is that this is the criteria for convergence. So the tolerance is set to 1E minus 4 with the requirement that 99% of the zones satisfy this threshold. In other words, for the model to be considered converged is when 99% or more of the zones or elements exhibit unbalanced forces below 1E minus 4. So that's the error of the differential equations that remains after solving the equations. So now that we understand this convergence criteria, we're going to leave it for factor of safety. That's the right parameters to use, and we're going to check save files and then also zonking. Okay, so when we're ready, so let's also time to set up initial conditions. So here in this case, we're gonna use lithostatic, so meaning that sigma 3 is vertical and equal to the density times depth, and the azimuth here is of the horizontal major component is 90, so east-west, and we can visualize it. We can visualize this tensor on the viewer. So let's have a look here. So I'm gonna have to hide the topo and pit shells. And then you can see here if we put ourselves in north position, so principal east-west, and if we also show the pit, you can see that the sigma 1 is perpendicular to the east and west wall. Now let's set up the mining sequence. Most of the time for open pit, you will use manual mining sequence because it's simpler. Basically, you have topo, nothing is mined, and then the second step is when you start mining the pit. But for many pit geometries or for gradual excavations or automated mine sequence, please check my other video where I explained how to stream that process. We only have. So in this case, we only have two steps: topo, where no pit has been mined, and when the pit has been mined out. What I'm gonna do here is we can simply go to the geometry plugin and then copy paste. So here in the second mining step, I'll just go to the geometry plugin and I'll copy the super pit, and then I'll save it. I'll copy it in the second step, and then my mining sequence is done. All right, so the next step is to define the pit region where factor of safety calculation will take place. So it's pretty simple. We only have to draw a closed loop with multiple points. So you'll see in a second how to do that. So I'm gonna go to the pit region. I'm gonna click on edit, and here I can start drawing my loop. So very important, this region, so that my IMAT doesn't calculate factor of safety everywhere. It's going to be time consuming. So I'm just really selecting the area of interest. Okay, so here I haven't done a good job, so I'm just going to actually redo it. I'm going to clear all, and then I'm going to expand my model domain. Click on shift, expand it, and then I can draw my zone of interest, okay, my pit region. All right, so here I go to the model domain, and for the model domain, this is where we can really check that will be our zone of Flag 3D. We can expand it. Okay, so this is the extent of our model. This is where the zones, Flag 3D zones, will be inside of it. So for refinement, I'm gonna go and create my zones of refinement. I start with a global cell of 20 meters. So that's the first level of refinement, and then I can create new refinements. New refinement name, region. I select pit region, and then I'm gonna go and select level 2. Okay, so what does that mean? Level 1 of refinement is gonna take that 20 meter and it's gonna divide the element length by 2. Okay, so that's level 1, and then for level 2 it's gonna further divide that edge length into another half. So we end up with a zone that has an edge length of 5 meter with level 2. Okay, so level 0, if you will, is 20 meter, level 1 is 10 meter, and level 2 is 5 meters. Okay, so I want in my pit region to have zones of 5 meters. Okay, obviously this is a tutorial, and we can go a little bit further than that. We can go like up to 1 meter. It's gonna be time consuming, but for demonstration purposes, let's leave it at 5 meters so our model can run fast. Okay, so let's create a new refinement for the weak fault zone. I will select polyhedron. Once we do that, we have to select the geometry in question. I go ahead and select structure, weak fault. Here we go. So that means that we're going to have a refinement level of 1, so 10 meter, that will be applied to the weak fault. Okay, it's pretty straightforward. Now it's time to define our material. So we have host rock, and make sure you select a plastic model, so more Coulomb. And then I'm gonna actually select the properties for that. I will give it some realistic values for open pit cases. And because I will, so I'm gonna create a new material. Okay, I'm gonna select material from a structure from geometry, north and south. Polyhedron. All right, and you see how it has created 2 material. Because I'm going to be only using one, I'm going to delete one, I'm going to select the other, and I can go ahead and select my geometry. So here north and south will have the same material. So I'm going to give it some realistic values as well, properties for faults. So for Young modulus 0.5 GPa, for friction angle 30, for cohesion 250 kPa, and for the tension 50 kPa. All right. So I'm gonna create a third material, which will be my weak zone fault. Okay. Here I'm just gonna double check. Here I'm gonna create, I'm gonna set up, I'm just double checking my properties. All right, they look good. All right, so I'm gonna create a third material, and I'm gonna, it's from geometry plugin. I'm gonna go and select my weak zone, and then polyhedron. And I'm gonna do the same thing, more Coulomb, and then I'm gonna give it some realistic geotech properties for fault zone. All right, looks good. Okay, I'm gonna rename the faults. I'm gonna say north and south fault. And then for the weak zone is good. For interfaces, basically I haven't created any, but we can create them with relative ease on IMAT. I'm gonna make another video for that, so stay tuned. And then so we move on to the water table, and we can select the depth. It's gonna be 5 meter. Okay, so now we are ready to build the grid. We have to check all the steps. So once we are ready, we have to check all the steps before building the grid. So construct the pit shells, construct the octree grid, apply the material, and say okay. So it's gonna start running, and we have 2 million zones and 2 million grid points. So if we need to increase that or to reduce that, we can always go back. And when we're ready to solve the model, we can either solve it on FLAC 3D software, or just stay in IMAT and solve it within IMAT. And there is a console, FLAC 3D console, so we can follow through the process of solving it. So for this case, I'm gonna say no. I'm gonna click on no. I wanna keep it in IMAT. And it's gonna start solving. So after a while, we can go and open the west wall. Like we can see directly the zones within the defined region get colored to look at the factor of safety. So here we have factor of safety contours. So you can see the mustard color corresponds to a factor of safety of 1.5. I can click and I can see the value here. Whereas the cyan would be somewhere around 1.6. So we can say that this west wall has a factor of safety of 1.5. We can also see the magnitude of displacement contours, and we can do a bunch of things. And then for same thing, we're gonna go to the east wall, and then we're gonna do the same thing. We're gonna go to factor of safety. We're gonna plot the contours. And then we're gonna select. It's very important to select the minus step number 2, and you can see here that we get a lower factor of safety, a 1.2, and we can conclude that basically the east wall is more critical than the west wall. So you can see how it's very practical to use IMAT for open pit modeling and factor of safety evaluations. I mean, the advantages are so numerous. Quick import of 3D geometries, great tool for simplification. When we have complex geometries like very high resolution structures or pit, or even CMS for underground, we can simplify them. No intersection problems or creation of extra volumes that we need to manage. Very streamlined process. Discretization is very easy and straightforward with the different refinement levels. Very easy, very intuitive. And same thing for definition of region of interest. You don't have to compute factor of safety because factor of safety are computational intensive. We can really just define small region to perform our calculations, and we can have multiple FLAC 3D projects on multiple walls. So that's how you should do it. So I hope this tutorial was insightful and that you learned tons with me. Make sure to stay tuned for more videos coming up.